Dominc, Nithisha, and Dhriti from Group 15 present to you the chemical context of heroin. We hope you enjoy. In this presentation, we'll be going over what heroin is, how it interacts with the body, specifically with receptors, and its long-term effects.
Meet Johnny, a recovering addict. As a teenager, Johnny struggled with drug addiction. However, he maintained sobriety and pulled himself through college, got married, and had kids. He was steadily gaining success as a music producer when he relapsed and got caught up with hard drugs, namely heroin. Within the next couple years, Johnny lost his job and contact with his wife and kids. Eventually, he sought help and is now recovering. We may not realize it, but Johnny's case is just one of far too many. Within recent years, opioid addiction has been on the rise, with related deaths occurring each day. As you can see, within the last year, 614 opioid-related deaths have occurred in New Jersey alone between the ages of 25 and 35. In 2016, 1,901 people died from opioid overdoses in New Jersey. Clearly, opioid abuse is a rising issue in the world. Heroin belongs to the opiate family, which means that it is a painkiller. Heroin, like opium and morphine, is made from the resin of poppy plants. Milky, sap-like opium is first removed from the pod of the poppy flower. This opium is refined to make morphine, then further refined into different forms of heroin. Here you can see that it comes in many different forms, such as white or brown powder. Heroin is highly illegal. Whether it's white heroin, black tar heroin, or brown powdered heroin, if you have it in your possession, then it is a violation of heroin laws, and you will be subject to arrest and prosecution. People inject, sniff, snort, or smoke heroin. Heroin acts as an agonist to endorphins. The primary function of endorphins is to block the transmission of pain signals along sensory neurons and to produce pleasurable sensations of euphoria.
When heroin enters the body, it is in its inactive form called diacetylmorphine. It is called this because of the two acetyl groups on its end, which make it hydrophobic. As it goes through the body, one of the acetyl groups are replaced with a hydroxyl group. This new molecule is therefore called 6-monoacetylmorphine. Finally, the second acetyl group is also replaced with a hydroxyl, making the 6-monoacetylmorphine into morphine, an overall hydrophilic molecule. So essentially, heroin and morphine are the same thing? Well, not exactly. Heroin is much more potent than morphine. But why? After all, heroin eventually turns into morphine anyways. See, the answer lies within heroin's hydrophobic nature that we previously discussed. In our body, we have a blood-brain barrier that separates the blood vessels from the actual receptors in the body. The acetyl groups of heroin, which are hydrophobic, pass through the blood-brain barrier very quickly. On the other hand, the hydroxyl groups on morphine, which are hydrophilic, take significantly longer to reach the receptors on the other side, and so heroin is more potent than morphine. Now, where exactly in the body are all the opioid receptors located? The answer, contrary to what you may think, is everywhere. However, they are mostly found in the brain, brainstem, spinal cord, peripheral neurons, and the intestines.
Morphine specifically binds to mu receptors throughout the body. Mu receptors are G-protein-coupled receptors, and morphine acts as a ligand that binds to a G-protein-coupled receptor. A G-protein-coupled receptor consists of 7 transmembrane domains. A transmembrane domain is located every time it crosses through the membrane. Morphine specifically binds to transmembrane domain 5. It acts as a ligand that binds to this membrane, causing a conformational change in the 3 intracellular loops, which trigger a reaction in the G protein.
And here is a 3D model of morphine covalently bounded to the mu opioid receptor at transmembrane domain 5. And here is a more detailed image which depicts the binding of morphine with the receptor. As you can see, the nitrogen in morphine covalently bonds to the receptor at the amino acid K233. However, this is not the only interaction that morphine has with the receptor. The yellow squiggles represent hydrophobic interactions, and the red lines represent polar interactions. When morphine binds in this way to the receptors on the neuron, two main changes occur. First, the calcium channels are closed off, and second, the potassium channels are opened. So, positive ions are leaving, and other positive ions can't come in to stabilize the charge. This leads to an overall negative charge within the cell. But what does a negative charge mean for the neuron? You see, a neuron needs to reach a certain positive charge to generate an impulse. In our case, the neuron remains negative, and so impulses can't be generated. Ultimately, the central nervous system shuts down. This results in respiratory depression, which is the main cause of opioid-related deaths. But how? Well, as we discussed, the neurons get blocked off, which in turn depresses the central nervous system. Because the central nervous system is in charge of regulating various functions of the body, such as breathing, its depression leads to the body's inability to detect carbon dioxide levels, and ultimately leads to the cessation of respiration.
When someone overdoses on heroin, you can use Narcan to reverse the effect. The thing about Narcan is that it only works if someone already has opioids in their system, which makes it ideal for overdose treatment. Due to its affinity for the mu opioid receptors, however, Narcan specifically only works when treating opioid overdoses, and not any other drugs. As we touched upon before, the excess binding of opioids to mu receptors in the brain can stop a person from breathing due to the body's reduced ability to detect carbon dioxide. The way Narcan works in this case is that it knocks the opioids off the receptors, which allows the body to detect and regulate carbon dioxide levels again, and in turn, breathe again. Extended use of heroin can also lead to addiction, and here's how it works. For the brain to experience pleasure, it releases copious amounts of dopamine. With this excess of dopamine, soon the nerve cells in the prefrontal cortex will communicate to the rest of the brain and actually start linking the pleasure felt from using the heroin to the heroin itself. Also, the body's tolerance for heroin rises with extended use. Over time, the brain adapts to make the pleasure felt as a result of using heroin less pleasurable. The use of heroin floods the brain with an unnaturally high amount of dopamine, as we mentioned before. In a person suffering with addiction, the brain is overwhelmed by this and responds accordingly by producing less natural dopamine or eliminating dopamine receptors. As a result, the person taking the heroin eventually has to ingest even more in order to get the same high. With prolonged opioid use, the body gets used to the effects that it is experiencing, such as a slower rate of functioning. When opioid usage suddenly stops, an addict can experience a host of withdrawal symptoms. For example, the body could rapidly expel waste through vomit or diarrhea. The hypothalamus, which is the body's thermostat, can go haywire, which causes unnatural sweating and goosebumps. And also, a sudden stop in usage means that there will be less dopamine in the brain because the natural production of dopamine will have reduced as a result of the abuse of heroin. This drop-off in dopamine may lead to depression as well.
Thank you for watching, and stay safe.